Hello and welcome. In this video, we are going to solve two more problems on kinematics from IE Irodov's problems in general physics. So in the first problem, it is given that there are two particles, 1 and 2, which are moving with constant velocities v1 and v2. At the initial moment, their radius vectors are equal to r1 and r2. We are required to find the relationship between these four vectors for the particles to collide. We are required to find the relation between these four vectors for the particles to collide. So we have two particles having position vectors r1 and r2 and moving with velocity v1 and v2. And let us assume that they collide at point A. For these particles to collide, they must reach point A simultaneously. So if these particles take time t to reach point A, then during this time particle 1 moves by vector v1 times t and particle 2 moves by vector v2 times t, such that their final position vector are same given by vector r. Therefore, vector r will be equal to r1 plus v1 times t, and this will also be equal to r2 plus v2 times t. Rearranging this equation, we can write r1 minus r2 as v2 minus v1 times t. Now what this equation means is that vector r1 minus r2 is a scalar multiple of v2 minus v1, and that scalar multiple is time t. So the value of time t will be equal to magnitude of r1 minus r2 divided by magnitude of v2 minus v1. This is the value of scalar time t after which the particles collide. Putting this time t in this equation, we can obtain r1 minus r2 equals to v2 minus v1 times magnitude of r1 minus r2 divided by magnitude of v2 minus v1. And rearranging it, we can write r1 minus r2 divided by magnitude of r1 minus r2. This is equal to v2 minus v1 divided by magnitude of v2 minus v1. This is the relationship between these four vectors which we were required to find. This is the relationship that we are required to find. In this next problem, it is given that a ship moves along the equator to the east with the velocity v0 equal to 30 kilometers per hour. The southeastern winds, the wind from the southeast direction, blows at an angle of theta equal to 60 degrees to the equator with velocity v equals to 15 kilometers per hour. We are required to find the wind velocity relative to the ship and the angle phi prime between the equator and the wind direction in the reference frame fixed to the ship. We are required to find the wind velocity relative to the ship and the angle phi prime between the equator and the wind direction. So we have velocity v0, we have vector v0 as velocity of ship with respect to the ground, we have vector v as velocity of wind with respect to the ground, and vector v prime as velocity of wind with respect to the ship. Using the theory of relative motion, we can write velocity of ship, velocity of wind with respect to the ground is equal to velocity of wind with respect to the ship plus velocity of ship with respect to the ground. In vector notation, we can write vector v is equal to vector v0 plus vector v prime. And rewriting it, we can write vector v prime as vector v minus vector v0. We can draw these vectors. So this is the vector v0 denoting the velocity of ship with respect to the ground. The wind is blowing from the southeastern directions, from the southeastern direction with vector v and making an angle phi equal to 60 degrees from the equator. The resultant of v minus v0 is given by vector v prime. So this is the velocity of wind with respect to the ship, and this is making an angle phi prime with the equator. So we have the relation vector v prime is equal to vector v minus vector v0. Now we can take x and y components of these vectors and use them in this equation. We will take the x direction as direction along the equator and y direction perpendicular to it. And we can see that for vector v prime, its x component is along the negative x direction and its y component is along the positive y direction. Similarly, for vector v, its x component is along the negative x direction and y component is along the positive y direction. Vector v0 is along the positive x direction and there is no component of vector v0 in the y direction. Therefore, taking the x component, we can write minus v prime cos phi prime is equal to minus v cos phi minus v0, and taking the y components, we can write v prime sin phi prime equal to v sin phi. Squaring and adding these terms, we can write v prime square times cos square phi prime plus sin square phi prime. This is equal to v cos phi plus v0 whole square plus v square sin square phi. Now cos square phi prime plus sin square phi prime is 1, and expanding this term we can write v prime square is equal to v square cos square phi plus v0 square plus 2v0 2v0 cos phi square plus v square sin square phi. Again, we can take from these two terms v square common, and using the relationship that cos square phi plus sin square phi is equal to 1, we can write v prime square as equal to v square plus v0 square plus 2v0v cos phi. Using the values of v as 15 km per hour, v0 as 30 km per hour, phi as 60 degrees, we can obtain v prime square as 15 square plus 30 square plus 2 into 30 into 15 into cos 60. This gives v prime square as 1575 and v prime as 39.7 km per hour. That means the magnitude of velocity of wind with respect to the ship is 39.7 kilometers per hour. Now using this relation, we can write sin phi prime as v sin phi divided by v prime. Now using the value of v as 15 km per hour, phi as 60 degree, and v prime that we have just obtained as 39.7 km per hour, we can get sin phi prime as 15 into sin 60 divided by 39.7. This will give sin phi prime as 0.327 or phi prime as 19.1 degrees. That means the wind direction with respect to the ship is 19.1 degrees.